Hi, I'm Jan. I'm the chief engineer for the Safe POSIX platform at BMW. I want to talk with you about Lola. It's one of one of the things that we did last year, and I want to start slowly with giving a little bit of what problems we try to address, and then I want to go into like how Lola is working and give you the key building blocks for it. Okay, so the first thing is like, what is zero copy, right? Why do we need it? And the main answer is it's for latency. And I took my little daughter here, Leah, like she likes to read books, I hope it someday. And the point is she wants to show her friend Ben like one line in a book, right? So she marks it. And then she goes, Ben is in the house next door, but Leah, like she knows computers, right? So she takes photo of each page and sends it to Ben. How long does that take? Ages, right? Would be way more better if she would just ship it to him, like just go to the next door, give him the book where the data was, right? And that is latency, right? Like the action of transmitting the data to the other side due to the copy of the information or due to the copy of the data, that is the issue which increases latency. And when we do zero copy, like we give the original data to the other side, we don't have the problem. Yeah. So why is that important? And now you learn all the new German word maybe, it's called Schrecksekunde, right? So what does that mean? I'm not sure if there's an English phrase for it, but it means like, if you're driving on the highway and you have to brake, have to do an emergency brake, for humans it normally takes around 1 second to realize that they have to brake and that they press the brake. And in this 1 second, And in this 1 second, depending on how fast you are driving, your car will take different meters. It will still drive different meters, right? So why is that important for us? We're developing computer systems, right, so they can be fast. But we've just talked about fail operational, and if you don't want to be fail operational because it's super expensive, you maybe want to react quite quickly, and you want to make some emergency maneuvers or whatever. And that's why latency is key in order for automated systems to work good. So let's talk about. So I'm the first one who's showing code here today, so please don't get afraid. This is AraCom, right? I'm not sure. I hope you've all seen that. And I want to show you how AraCom supports this use case after all, right? Basically, here at the beginning, we have a little bit of like the infrastructure. We want to offer a service. The service is called big data, because all of this only makes sense if we want to send big data, right? Of course, I wanted to do something with autonomous driving, so that's why we have some lanes, and we want to say, hey, how is the lane condition? Is that good? Is that bad? And we're in the US, so you have a lot of lanes. That's why it's big data, okay? So basically what we say is we first have to offer the service, and then we can send the data. And here's now the important point. We first allocate the data. And this is now the main point, okay? We have a vector or an array, you name it, and the memory is not owned by the application. Or is not provided by the application. The memory is provided by our middleware. And this is where AraCom comes in place, and AraCom says, or the user tells AraCom, hey, give me some memory where I can use to send data, and then we basically operate on this data here. And then the user says at some point, okay, you know what? My little daughter Leah, she said, I now marked the paragraph in the book, right? Here you go, and you transmit it. And that's basically what we do here. And this is the idea how AraCom basically supports the zero copy use case. So basically you have to implement that. But before we go into this, how we implemented it, I want to talk one step more about what is a mixed ASIL setup. Mixed ASIL setup means, we've heard it today more often, you have one part of your system which is in another safety level than other parts of your system. that does not necessarily mean that they don't have to talk with each other. Of course, you can still use information which is not QM and make it ASIL with additional data or whatnot. But the main point is really they want maybe to talk with each other. Yeah? And now we have to ensure freedom from interference. That's the name that the ISO 26262 gives you. And what does it mean? And the important point is we need to ensure freedom from interference between the processes, but we will not do any qualification of the information that is sent. Okay, that's quite important. So we don't care what the user sends. It's the user's responsibility that he ensures the data that he is sending is not affecting any safety goal. We are only taking care that we don't break freedom from interference between the processes. And this is why. This is why I'm saying this. So how can you do zero copy in a POSIX operating system? The only way that I know, maybe you know another one, is with shared memory. But before we talk about shared memory, let's shortly look at how does the memory setup look like in a POSIX operating system, yeah, for a process. So we have two kinds of memories. The first kind is the physical memory, right? So it's this part that you plug into your computer, the RAM, the random access memory. And if you need more, you have to plug in more, right? But the fact is that each process has a so-called virtual address space. So each process thinks he owns the whole physical memory. Of course, you can configure that and everything, but just for the sake of having a model in our minds. So basically but how it's really looked like is that we have another process, so I took the other color for it, and this other process has other parts of this physical memory, okay? And this is now the point that the process thinks he owns everything. We have then the different sections, the stack, the heap, and where our code is stored, which is the data that is used. And the big idea of shared memory is now that we basically have one part in this physical address space, and this part is actually used by both processes. That's what I tried to show with the color coding. But check it out where the stuff is stored in the virtual address space. So you all know, I hope, what pointers are, right? So if you have a pointer to a variable A on your stack, the pointer is the address in the virtual address space. It's never the address of the physical address space, okay? And this is now the interesting part, because whenever you are mapping this shared memory into your virtual address space, it is not ensured that it will be mapped at the same address. And that's a key point, because that means a pointer that is stored in here in the shared memory will get invalid when you have it in another process. So how can you have more complex data types in there? And the answers are offset pointers. So basically, we don't store a pointer here, but we just store, hey, this one entity is 5 hops away, okay? That's what we're storing, and that's what's called an offset pointer. Why that's important, you will see it later. So how is the basic structure of LoLa? And LoLa stands for low latency, if I did not say that yet, because that's what we're trying to achieve. So basically, in this setup now, we have different processes in the mixed critical setup. In this case, the producer process is ASIL B. We have one QM and one B consumer. What we now need to ensure is that this book that my daughter gave to our guy living next to us, that he is basically not altering the data, right? Because if multiple people want to read in the same book and he is destroying the data and he's marking something different, then we don't know what is right or what is wrong. And this is the main problem when you use shared memory in a mixed critical setup, because you have to ensure that the data is not altered. That's why we split it this here into 2 parts. Oh, sorry, wrong button. That's why we split this into 2 parts. The first one is the data, which is basically read only by the producer. So we put the data there and we leave it there. The only one who can alter it is the producer. And then we have control data, and I will go later into how this is organized to basically elaborate on and have some housekeeping for the sample data. There are other parts in adaptive AutoSAR which will require still some kind of notification mechanism. So we've looked into this, and you can implement this notification mechanism with shared memory. That's not a problem. But it's a lot of work without big benefit, because the big benefit is that you have the data at one place, the zero copy, because that's what costs you, okay? And then you can use still the operating system for notifications, and you get this freedom from interference for free. Okay, and this is now the main point, so lock freedom. Just imagine, and that's also one of the reasons why we basically took a notification mechanism from the operating system. If we would have a mutex, or what is a mutex, right? We need a mutex to ensure that the critical sections of two processes work on the same thing, that they don't destroy each other, right? That's why we have mutexes. The problem with mutexes is they need to get locked. So what if the QM process is locking this mutex and he's never unlocking it? There would be no possibility just like that for the ASLB process to take the ownership and work on the data. So freedom from interference is gone. That's why we said, hey, let's use lock freedom. And actually, this is a term that's used in computer science, but it's not totally true. It's a lie. We still have locks, but we have hardware locks. So basically, we're using atomics. And you can see this example here. On the left-hand side, we basically have this mutex approach with two threads who are trying to access the same data. And here on the other side, we have done that basically with atomics. So an atomic uses the hardware to basically show or to basically synchronize the access. The fun fact here is, how does this work? You basically have to check if the data has been altered at the end. But at the end, the main point is the hardware ensures that there is nothing wrong, right? If you have enough ASIL level in your hardware, which you need anyhow, then it's ensured from the hardware that this will work for you. But this comes with a cost, because lock freedom is hard to achieve. And this is where we go into the algorithm. And this is where we just have seen the data section and the control section, okay? So we have looked into multiple data structures on how we could have organized the control data. And we were going super fancy. Yes, that needs to be a map, then we have this and that. Yeah, but implement a lock-free map. There are a lot of papers out there. You can try to read that up. And at the end, we did some measurements. And this is the most performant one, because how many events do we have, right? How many events do we have? 10, 20? But it's not 1,000 or something like that, at least not for our use cases. It can be different in yours. But that's why iterating over the control data and just searching is for us way faster than having a sorted data structure itself. So, but let's look into this. Basically, we have split up the two blocks of memory that you have seen earlier into slots. We call it slots. And what is a slot, right? A slot is basically when you send, then it uses one slot. So you say allocate, you get a slot. You send, you free the slot. That's the idea of it. How do you know how many slots you need? Well, each adaptive application can subscribe to one of your events, right? So you have the subscribe call there, and has to say how many events he wants to subscribe to. And this way, basically, you always know already in advance how many slots you need. That's a configuration parameter that we have. And I mean, I just want to make that clear. This is now a trade-off, right? Because we have higher memory consumption because of this. Or do we? No, we don't. We don't have higher memory consumption because if you still would use the copy, you would still have the slots in each application, okay? So basically, we have application 1 that needs 2, application 3 needs 3 slots, and then we have 2 other ones for the next application. The only additional memory consumption that we have, and that's in our algorithm, is that we always need n+1 memory slots, because you always want to ensure that the sender can allocate the next data. So that's why, yes, we have an increase, but in my opinion, 1 slot more is worth it. But how does this work? And this is now where we come again into this atomic operations stuff. So I said we are using atomics, and atomics are using hardware support. And like, it depends on the hardware how much byte they can store. And if you have a 64-bit system, it can store 64-bit because that's how the registers are. So you will never be able to store like data which is bigger than a UN64 as of today in a log-free manner. Yes, there are other papers out there, but you have no real hardware support for other approaches as of today. So that's why we need to get a little bit fancy, and basically we need these states here, or this data, for each of these slots in order to do our algorithms that you can see them here. I mean, they're super abstracted, but just for the sake of explaining it. Basically, in adaptive AutoSAR, you can use, you have different opportunities on how you can find events and so on and so on, and that's why you need this timestamp, and we need the state to know if a slot is right now allocated. And then we need this use count to see from how many consumers this is right now allocated. Because you just have to imagine you have one process and he runs on a cycle of, I don't know, 10 milliseconds, and you have another one who runs on a cycle of 1 hour, right? So this dude which takes 1 hour would occupy a slot for 1 hour, and that would be totally fine. So you cannot synchronize this up. Okay. And now I come back to this point where I've talked earlier about the offset pointer. Because we have one problem with this shared memory approach. We've now talked about 3 things already that we needed to do in order to ensure that freedom from interference is given. One was we don't use mutexes, and the other one was the split between read and write on the data. Yeah. But there's one more thing. So we have these control sections, right, that we've talked to, and these control sections could get manipulated because our algorithm needs to access both of them. Or if you have a QM producer and she's just writing garbage in the shared memory segment, then this could lead to an issue. And what could this issue be? Basically, what could happen is that if we have a pointer here, then we could jump out of the shared memory segment and thus use data which, or even alter data which is not part of this shared memory region. And that's actually the biggest problem that could happen. So malicious data in the shared memory segments could be used to alter other different data. And that could happen, and that could basically destroy freedom from interference. And in order to avoid this, we're using something which we call active bounds checking. And I'm not sure if you know, for example, address sanitizers, but they work quite similar, but they just instruct the whole part of your code. But we don't need to instruct all part of our code. We don't need to check everything. We just need to check on each dereferencation of an offset pointer if the pointer is still valid. And that's basically like the idea that, like, super simply explained. Each time when we open a shared memory segment, we will have a singleton and a runtime. We have AraCom runtime anyhow, where we basically will remember that this shared memory segment exists. And because we're mapping it into our virtual address space, we know the start and the end of it. So we just store this in a map. And then we will basically go ahead and on each dereferencation of our offset pointer, we will basically do a bounds checking. So how can this look like? It could look like we go into here, we check like if it is in the range, And if we found something, it is good. And if we don't find it, then we have an issue. Of course, that's not fail operational, but that's also not what we need right now. We just need to be, we will go basically into a safe state if that happens. And for us, that means crashing. Yes, and with that, that would be basically the third kind of safety measure that we, for example, took in order to make shared memory ready for mixed ASIL setups. And with that, thank you.